I'm going to focus on radio frequency tomography. The key word here is tomography. Our long-term vision is really very simple and very straightforward. We do know that in the modern communications and sensing and navigation environment, spectrum being at a premium is going at ever-increasing rates to the highest bidder, okay? And so I used to work for the government, and so, you know, for 30 years I would see the erosion of government spectrum allocation to DoD, and I would think, oh, this is outrageous, this is ridiculous. There was a study done. It was published in 2014, and the data was from 2012, I believe. I'd have to check those facts. I was going to look that up while I was actually waiting to talk, and then I got so intrigued by the discussion on cyber, I had to listen. The auction at the conclusion of the calendar year 2012 had raised $43 billion. By 2014, that spectrum allocation to non-governmental users selling commercial wireless had raised $104 billion that year in state and local sales taxes across the USA. It's all about the money. It's not as exciting as cybercrime, but it is all about the money. So we're in a big crunch in this country in this sense. Spectrum is at a premium, and it's going to go to the highest bidder, and the highest bidder is not national security or state and local governments, it's commercial wireless. So what we're trying to do then is to develop some technologies around this tomographic principle of operations that says that if you can use enough spatial degrees of freedom in a sensing environment, you might be able to get away with very little bandwidth. You might be able to get away with almost no bandwidth at all, so-called ultra-narrowband. That's a pipe dream. It's a good one, but you know it may be some number of years off, but we certainly got to go down that road. So tomography, formal definitions, many of them. This is one that's non-mathematical, so we could talk about this idea of imaging in sections, and the objective then, of course, is to accomplish this using, in the case of, say, medical imaging, penetrating waves, right? But, you know, the applications are just huge. I only list a couple of them here that are kind of interest to me. Archaeology, I really want to go do tomographic imaging of the Great Pyramid. We almost were going to do that before all the troubles arose. We had some money from an agency in Europe to go do that, and then everybody said, you know, hold off. I still want to go do that. That would be fun. That would be really neat. If we could do tomographic imaging, you know, same thing that we do medically to the human body, but do it to the Great Pyramid or to the Sphinx, that would be exciting. The other thing that we really want to do is to apply these concepts in tomography to atmospheric sciences. So in this area, we're prone to problems with, you know, localized weather events that turn into tornadoes. They certainly do damage. They can be deadly. Are there things one of the ways that we study these localized weather phenomena is through something called persistent surveillance. So not only if we do it using conventional approaches, not only do we need lots of bandwidth, but we need lots of radars steering in lots of directions all simultaneously. That's the same spectrum that they just sold off for $43 billion and raised $100 billion a year in revenue. Guess what? Understanding, studying, solving issues with tornado formation, not a competing priority when it comes to the money they raise in sales tax revenue. So the CAT scan, right? So I love this picture. There's a medical research institute, animal research center in Germany. They just acquired a year ago, maybe it's a little more than that. I was supposed to go to their grand opening, and I never made it, but you know, they're literally buying the latest and the greatest sensing technologies to assess the health and wellness of wildlife as a function of their changing habitat. Well, these machines, you know, CAT scans, MRI machines, that's fairly mature technology, fairly well understood, but it's in a very controlled environment, right? The lions put to sleep, the tiger, you know, I mean, whatever animal they're assessing health and wellness of. So we don't want to do this indoors only. We want to do this out of doors. And so we have a big issue, and that is how to make this technology robust with respect to operations in real-world environments. So from a U.S. National policy perspective, we've seen a recent resurgence in manufacturing, mostly due to economic considerations that are really outside the immediate control of the U.S. federal government, but certainly impacted by government financial policies. But, you know, for the purpose of materials and manufacturing, there are potential applications that I think are huge. Health and wellness. Can we create an RF tomographic portal, something not unlike a doorway, that someone simply can just walk through and we can assess the health and wellness of the skin tissue, early detection of skin cancers, save lives. RF is cheap, right? RF components are really cheap. MRI machines are millions of dollars. CAT scan machines are millions of dollars. If I leverage the parts that are being used by the commercial wireless industry, we can build a portal around this doorway here for just, you know, a few tens of $1,000s in the price of parts and computing. Some of my students are here. We've been building a lab over in ECE for the last year and a half or so. We've been trying all kinds of neat and clever things. They'll tell you the price of parts, the RF parts, they're getting cheaper and cheaper and cheaper. We could do this. But the goal, health and wellness, potentially a very big deal. A lot of where RF tomography came from is in safety and security, especially facilities protection, runways and the like are really of keen interest, especially to our military. Right now they're looking at how we're going to sense the conditions of runways that have been previously been abandoned. If we have to fly into areas, they're looking for technologies. Tomographic approach that looks into the ground and below ground imaging technology has great applications. And I already mentioned tornadoes, atmospherics, and the like. So we're really very much oriented right now in our thinking and in our research towards this whole idea of calibration, first and foremost. If we don't know why we're getting the images we're getting, then we can't improve upon them. And so that's where a lot of our thinking is going at this time, in this day and age, at MUMA Lab, at Kettering Labs. Yashar is focused very much on the calibration of below-ground imaging. Ali is very much focused on the calibration of the sensing of the orientations of objects that might have straight edges. So things that we might think would be awfully easy to image, but how do you image them well in a cluttered environment? How do you find that one wire that's indicative of a problem in a machinery application or what have you? And we're doing other things along those same lines. Another student, Nihad, is looking at dynamic imaging, imaging to the object as opposed to the point, the way conventional tomographic imaging works for medical applications. So I'm driven in my thinking very much by the remote sensing applications. I really want to go after this tornado problem because we can save lives. We're looking at using really cheap marine radars, making improvements to them so that we can do things like multi-static sensing for tomographic imaging. Another student in the back here today, Hamdi, is working on just that problem. He's figuring out a way to make relatively affordable marine radars, $5,000, with another maybe $5,000 in FPGA technology, fully coherent, and therefore competitive with coherent off-the-shelf marine radar that might cost a couple $100,000. Now we could start to talk about putting a marine radar that's been modified maybe on every cell phone tower. Wouldn't that be neat if we could do that in this area and really truly study weather phenomena? And also support other national and state and local interests as well. Everything from air traffic control, to maybe the assessment of say, weather conditions, rain formation, and what have you. Neat databases. There's the picture of the marine radar that's up on the roof. Well, actually, we took it down to modify of Kettering Labs. We are also looking at how we might apply these same sensor systems in, not so much in the USA because we're lucky. You know, yeah, we have some economic problems, but we're still the wealthiest nation on earth by most measures, right? We really are. So we have wonderful air traffic control in place. But what about third world countries who can't afford a $25 million air traffic control center? Can we help them? Can these modified technologies be made to function and work for the purpose of making airports safer around the world in the poorest of poor countries? That would be a wonderful humanitarian contribution. And of course, you know, we're visual creatures. We don't want to just see a dot. We want to see, you know, an outline. We want to see the face of the pilot. Well, that's not quite where we're at. Okay, so close-in sensing. One of the real big drivers in RF tomography for the short term for us is this idea that we want to be able to look into buildings. I'll give you an example, a very simple one. Can we apply very cheap, very affordable, almost throwaway RF tomography to buildings like schools or hospitals or nursing homes, right? Retirement communities. When there's the need for evacuation, can we reliably say all human occupants have been evacuated? And by the way, another tool in our toolbox to do that, not just videography, snapshot photography, but RF tomography, where we can actually sense the motion of individuals as they evacuate a facility. That would be a lifesaver. That would be really neat. We are looking at below ground imaging for a lot of applications. Obviously, one of the things that's driven this country and Europe in the last 10 or 15 years is the idea that there may be weapons of mass destruction buried somewhere. I'm sure there are. But more important to me is I want to solve the problem of how do we find, for example, sources of clean water in, say, the Southwest. We could help a lot more people by doing those kinds of things. They have a lot of issues with the sensing for the purpose of mapping out where water formations may occur, where they dried out and when. And there are a lot of people using monostatic or pseudo-monostatic radar applications to assess those below ground conditions. We certainly want to apply RF tomography. This whole idea of circular SAR, can I take a really affordable imaging radar and fly in these great circles around and around and around an area of interest? This goes back to the World Health Organization, 1974, circular SAR. What they were doing to help poor nations in Africa, they were flying SAR in these circular modes for the assessment of crop production potential. We could do a much better job with RF tomography. You'll see why in a minute or two here. Here's another interesting little concept. This is a friend of mine, unfortunately since passed away. This is a database produced by NIST. This is X-ray computed tomography of a rose. And then when you use prior knowledge, when you use knowledge about the nature of the rose or the below ground structure or the tornado in its early stages of formation or what is indicative of the early stages of cancer formation in the skin, you can do a much better job. Russ did this work pretty much by himself. He had 10,000 priors, but what he did was he basically went and took all of the data he could find on the formations of stems, branches, leaves, petals, pedestals, all that stuff, put it all into his database, and like he said, this was a fragile solution. It wasn't the most robust imager that he could develop, but he got an image that looked a lot more like a rose than what you get using conventional tomographic imaging approaches. Really neat. Why can't we do that for skin cancers? Why can't we do that for tornado formation? This is the kind of research we're trying to do in our lab over in EC and over in UDRI SSD. This chart is just to let you know that research at a serious level in tomographic imaging has been around for 100 years. There's probably 1,000 key players. I just show a few pretty pictures here. Well, maybe not so pretty. A few pictures here. But, you know, there's a lot of active research going on right now. Been going on for 100 years. How does tomography work? Very simple. If you can cast a shadow on an object and collect those shadows from different viewing angles where the source of the shadowing is controlled, then you can reconstruct what that object might be by essentially using back projections. Sounds simple. We want it to sound simple. There's all kinds of math tricks that you might use, but the idea, of course, in tomography is it's not just the optical shadow cast by an object, but in fact the transmission of energy through an object, the scattering of energy off an object. How do you collect that energy? How do you use it to figure out what's inside the object? That's where we're going. Yeah, here's some primitive math. You know, this is a famous picture you'll see every now and then in a medical journal. Shep's image here. You know, they had basically been looking at formations of disease, and what was happening was there was obscuration due to focusing errors and an auto-calibration. They called it auto-calibration defeat. So that basically is they made their auto-calibration so sophisticated it was self-defeating. I don't know all the particulars. I do know that if you go look in the medical literature, you'll see this appear again and again and again, and they'll always use the same remark. When you make your algorithms too sophisticated, those darn researchers screw everything up. That's not quite fair, but that's what they say. So, but what we really are looking at, and there's no math here on purpose, is we really want to look at not just how we go to form an image, you know, detections, locations, orientations, but also how we exploit other observables. For example, if someone has a piece of metal in their body, say some repair work, and at the right radio frequencies, that metal object has a resonance. We ought to be able to exploit not just imagery of shapes and sizes, but resonances of objects, and not just metallic objects. So we're really looking now at this all-inclusive theme for how we assess, in the case of a human, the health and wellness, not just of the body as a whole, but individual functions within the body. So then the other thing that I really want to bring to this table, you know, my colleagues tell me, let's get some of these other problems working first, but we're kind of jumping ahead. I'm jumping ahead. Maybe I'm jumping off, I'm not sure. But, you know, we really want to bring some of this perspective that emerges in so-called big data analytics, in cognitive processing. Better word for cognitive processing is educated guesswork. And if it's not educated, then it's just guesswork. But, you know, the human is an unbelievably powerful machine when it comes to solving problems. We can't capture even a fraction of the essence of what makes us good at problem solving, but we're moving in those directions. We also want to capture some of that. For example, I talked about the fact that we might want to use resonances. So what's some of the cognitive processing that might be appropriate in the application, say, to earth tomography and other forms of sensing the condition of a human? Well, the record keeping of a patient. If a patient's been in and out of doctors and hospital care for a decade, there's lots of records. Subject to error, not perfect, but it's prior knowledge. How do you react? How do you act and react to that kind of prior knowledge? And how do you react to the fact that everybody's the same except we're all different, right? We all have arms and legs and eyes and nose and mouth, right? And they're all kind of there, but the shapes and sizes, the textures, they're a little bit different, maybe a lot different. But this whole idea of cognitive processing in advanced algorithms is a potential game changer. The previous speaker spoke about cybercrime and cyber terror. Cognitive processing is potentially a very big player there because you can talk to the players in cybercrime. And I used to do a little bit of work in this area. And they'll all tell you, we knew we were going to be hit. So one of the things we used to do in cybercrime was put up what we'd call a fishbowl. Put a computer out there and give it the visible IP addresses so that it attracted the cyber criminals. so this is not just applicable to RF tomography, or CAT scan, X-ray tomography, or magnetic resonance imaging, or air traffic control. It's a very broad, very robust area that can be cherry-picked over the next dozen or so years. But we've got a lot of work to do to make a meaningful contribution. So we're talking about tomography, spatial and spectral diversity, as compared to synthetic capture radar. The problem with synthetic capture radar, with all of these conventional approaches, is they use lots of bandwidth. Government just raised $40 billion a few years ago. State and local governments are raising $100 billion plus a year on taxes. We're not getting that bandwidth back. This image of the University of Michigan Stadium was collected in a band that now has been partially auctioned off over the last dozen years or so. So, a friend of mine from Buffalo, Merdad Sumek, did some work years ago where he looked at, with relatively narrowband imaging techniques, if you use full geometric diversity, you can get a much better indication of what the target is like. I mean, no matter, and like Merdad would tell in his audiences, they would always be curious about this. Well, would more bandwidth help? No, because you've got blockage. So, spatial, spectral diversity, geometric diversity, very important. And I already mentioned a dozen times already that we're losing bandwidth. So we don't have that bandwidth. Even if it could help, we're not going to get it. So we built a lab in Kettering. And we have some robots, we have some antennas, we have a number of tests ongoing, one of which I mentioned already is ground penetrating radar. The idea is these motorman robots having antennas, even targets on them, very, very much provides for tremendous spatial degrees of freedom, geometric diversity. And so the idea is to, of course, probe under a number of conditions. Here's the first. I tell people this was my Christmas present from Ali and Yashar. So I was drinking on Christmas Eve last year. They were working, and they produced the first real image. This is ultra narrow band, 1 kilohertz of bandwidth at 8 gigahertz. Here's a FECO-based simulation of this pipe that was laying on some blocks of foam. Here's an ultra-narrowband tomographic image. You can see what they picked was one of the harder sensing geometries. This is the so-called forward scattering geometry. Probably not the one to start with because it's the hardest. Look what they did. They got an image. Is it a beautiful image? Guess what? If you're a radar person, that's a beautiful image. If you're not a radar person, just lie to me and say, oh, isn't that beautiful? But what they did is they used this geometric diversity to get these slew of angles on transmit and receive to be able to produce this, which is relatively well comparable to the simulation. It's really phenomenal. First result, beautiful. I mentioned below ground imaging. I got to speed it up here real quick. We're looking for Department of Energy. In this country, we've got 140,000 miles of high-power transmission lines going to be replaced over the next 25 years. How, when, and where, and why to place towers, what force we can evade, all that is all up for grabs. And we have a small contract from ARNet being funded by DOE to look for the health and wellness of trees. Why? Because if you're going to plant a tower for a 500-foot transmission line in the middle of a healthy forest, and you can move a quarter mile over and go into an area that's already been devastated by disease or what have you, you would do it, right? We don't have convenient ways to correlate large databases with localized databases about the health and wellness of trees. Here's a result that Yashar produced very recently, just burying some dowels, wooden dowels, in sandbox to see, people just form an image. Right near the surface, though. It's easy to image deep below the surface. Here's an experiment that I did a number of years ago. We were looking 100, 150 feet into the ground. That's actually an easier problem than looking at tree roots an inch to a foot deep. Much easier problem. Here's some experiments we did on ultra-narrowband tomography. It works, it works. Now we got to make it work robustly and work in the real world. I mentioned dynamic imaging, imaging to the object as opposed to the point scatter. Here's a piece of wire lying on the ground. You know what, that should have been moved up a little bit further. But you can see here, using some algorithmic instantiations that are a little bit cumbersome. It's polarimetric, It requires a moving platform to exploit range Doppler coupling. But you can see here, we're imaging, in this case, a piece of wire on the ground. I already mentioned the work of Ph.D. making a cheap marine radar fully coherent. The idea, and he's already done experiments capturing data, trying to coherentize this radar by capturing the transmit waveform, pulse train, and then cross-correlation processing with the receive pulse train. Okay, we're almost there. In the end, it's all about the processing. What all of this means is really very simple. Yeah, I used RF tomography because that's fun. It's actually something I know something about. But in the end, what it's all about is so-called big data analytics, exploitation of big data. That's the path we're going down. In our lab at UD, we're lucky enough to have one of the preeminent image processing, video processing guys, Dr. Asari. He was just here. We have some other great folks in EC. We're working together for this common goal of big data exploitation, big data analytics. It's all about the processing. If we can get the algorithms right and know what data to look at and what data to ignore, we can do really great things.